Hi, we're now ready for our first real growth model. And this is actually going to be a simple one. It's a simple growth model, but it's still going to be far more complicated than any model we've seen so far. It's going to have all sorts of moving parts. That said, still by economist standards, by the models that economists use today, it's still relatively simple, right? So let's hang in there. So here's how it's going to work. Our model's going to have a group of workers, and there's going to be these coconut trees, and the workers can pick the coconuts. Now, when they pick the coconuts, they can do two things with them. They can eat them, because they're good, right, and drink their milk. So they live off these coconuts. And they can also, instead of eating the coconuts, use the coconuts to build machines, right? And these machines can help them pick coconuts even faster. Now, there's one other assumption we're going to add in, right? These machines will wear out over time, because they're made out of coconuts, right? So they're going to sort of degrade over time and have to be replaced with new machines. So that's it. Very simple economy. Right? Coconuts, workers, machines depreciate. What we want to do is construct a model of that, and we're going to use that model to explain the role that investment in capital, in this case the machines, produces growth, and the limits of that. And then from that, right, we're going to see why innovation is so important. But for now, we just want to focus on this very simple model, right? So let's get started. Lots of moving parts. Tons of them, okay? So hang in there. So there's going to be workers at time t, so we're going to call those L of t, so those are the laborers, right? Then there's going to be machines at time t. We'll call that M of t, right? And the reason you put those t down there, those t's and those subscripts t's, is because over time there's going to change, right? There'll be the workers at time 1, workers at time 2, machines at time 1, machines at time 2, and so on. The workers and machine are going to combine to form output, right? And we're going to call that O of time t. And then there's going to be, when you think of those coconuts, remember they can be eaten, that's E of t, or they can be invested, that's I of t. And when I say invested, that means they can be turned into more machines. Now, to figure out how many are eaten and how many invested, there's going to be a savings rate. And the savings rate will determine, like, the percentage that we put in savings, which goes into investment, and then the percentage that we don't save, which we just eat, and that's E sub t. And then the last thing in the model, I realize this is a lot, is this depreciation rate. And that's the rate at which these machines wear out. We're just going to assume that some fixed percentage of the machines wear out each period. That's a simplification, but we're going to use it. All right? So lots of stuff. Workers, machines, coconuts. The coconuts get eaten and turned into more machines. And there's depreciation. Now, we've got to make some assumptions. The first assumption we're going to make is that the production of these coconuts is increasing but concave. Remember, we had concave functions going up and sort of falling off in both workers and in machines. So that means the more machines, the more coconuts, the more workers, the more coconuts, but those things sort of fall off, right? And we're going to use a specific functional form that says it's just the square root of the laborers times the square root of the number of machines. Second assumption. Output is either consumed or turned into coconut or machines, right? So the coconuts are either eaten or turned into coconut picking machines. There's no waste. So basically then that means output O is just equal to E plus I, right? And E is just the amount we eat, I is the amount we invest in the more machines. And another way to write this is just to say that I is equal to S times O, right? Because S is our savings rate, O is our total output, so the amount we invest is just going to be equal to our savings rate times the output. And then the last thing is these machines depreciate, right? So the machines we have at time t plus 1 is going to be the machines we had at time t plus our investment minus however many depreciate, okay? So again, lots going on, right? We got all these variables, and then these are the equations that help us make sense of those variables. Okay, let's step back on that first assumption a second with concave. So concave means that, like, the first workers, gives you more coconuts. The second gives you more coconuts, but it gives you fewer coconuts than the first one did, so it sort of falls off. So economists call this diminishing returns to scale. Here's a picture. So if this is the number of workers, and this is the number of coconuts for the C's, what you can see is the first worker gives you quite a bit, the second gives you fewer, and the third gives you sort of even less, right? So what you get is, as you add more workers, you get more coconuts, but the workers become less and less valuable. And the same is going to be true of machines. Okay, so that's all concave means. Okay, we have a lot going on here, right? So let's simplify things a little bit. Let's assume that we've just got 100 workers. So remember before, our output was equal to the square root of LT times the square root of MT. We're going to assume we have 100 workers, so that's just going to mean it's this 10 times the square root of MT. That'll make things simpler. In a more realistic model, right, we'd have workers deciding to go to work depending on what the wage is. And so we'd have to create a market for wages as a function of output and as a function of how much people like the coconuts, and that would get really complicated. So we're just going to skip all that stuff. We're going to skip the entire labor market and just assume everybody goes to work every day and then we'll see what happens. Okay, so let's do an example. So now we're going to do some math, but we'll try and do it slowly. So what we're going to do is assume that the depreciation rate is 1/4 and the savings rate is 30%. And let's suppose we start out with 4 machines. So we started with 4 machines. The output is just 10 times the square root of 4, which is 20. So how much do they invest? Well, remember they invest 20 times 0.3 because they invest 30%. So that means 6 machines. So investment is going to be 6. How much depreciation is there? Well, depreciation is on the old machine. So there were 4 machines in the past. 25% or a fourth of those get worn out. So that means that's 1. So depreciation is 1. So we subtract those two, and that means we're going to get a net of plus 5 machines. Right? We had 20 machines before. We're going to invest in 6 new ones. We lose 1 to depreciation, so that gives us 5. We started out with 4 machines, so that means in year 2 we've got 9 machines. Here's how our economy worked. We had 4 machines, we produced 20 coconuts, we ate 14, we invested 6, we lost 1 machine to depreciation, and so now we have 5 new machines, right, the 6 minus the 1, and that gives us a total of 9. So now we start out with 4 machines, now we get 9. So we had a nice GDP of 20, and now we've added more machines, so we should do better. So let's look at the next year. Next year we've got 9 machines. So output is 10 times the square root of 9, so that's going to be 30. And let's think about how many new machines do we get? Well, we're going to take 30 times 0.3. That's how much we save. So that gives us 9 new machines we're going to buy. But the question is, how many do we lose to depreciation? Well, we had 9 machines, and we've got to multiply that by 0.25, so that's like 9 over 4. So that's 2 1/4. Let's just simplify this, and let's just suppose it's 2. Okay, so depreciation, we lose 2. So 9 minus 2 is 7. So we had 9 machines to start. We get 7 new ones. Now we've got a total of 16 machines. With that little fudge for the 1/4 we put away to keep the math simpler. Let's look at our GDP, right? The previous period, our GDP was 20. Now our GDP was 30, so we've got this nice sustained growth. Okay, let's look at year 3 now. Year 3, again, with our little fudge factor, we've got 16 machines. So if we have 16 machines, that means our total output is going to be 10 times the square root of 16, which is 40. So what's happened to our growth? We start out with 20, and then 30, and then 40. Actually, a little less. You know, remember we have that little fudge factor that we included where we should have subtracted 2 1/4. But we get this nice sustained growth. Now we could ask, is this just going to continue? Are we going to go from 10 to 30 to 20 to 30 to 40 to 50 to 60? Or is it going to fall off, right? Well, we see a hint that it's falling off a little bit because this number, again, remember, shouldn't be quite 40. It should be a little bit less than 40. So you said to go to 20 to 30 to a little less than 40. You can start asking, are there limits to this growth? Well, to try to understand whether growth would stop or not, let's do the following. Let's assume we have a big number of machines, a really big number, and see if it just continues to grow or to see if something different happens. So let's suppose we have 400 machines. So if we have 400 machines, our output is going to be 10 times the square root of 400, right? So that's 10 times 20, which is 200, right? So that's great. That's huge GDP, right? Huge output. What's our investment going to be? Well, we had 200 machines. 200 is our output. Our savings rate is 0.3. So that means we're going to invest in 60 machines. But depreciation is going to be 400 times 1/4, right? So 400 machines, we're going to lose a fourth to depreciation, which is 100. So we're investing in 60, we're losing 100, so that's minus 40. So if we started out with 400 machines, we'd fall off to 360. So wait a minute. So now we see, wait, somehow this economy is going to grow, but it can't grow this big. If it grew to 400 machines, we would shrink back down to 360 machines. So now we got to think, but wait a minute. Is there some number it would reach? I mean, if we started with 4, we go from 4 to 9 to 16 and so on and so on, and it looks like it's never going to stop. But then we said, well, what if we had 400? Would it continue to grow? And we find out, well, no, it's not going to continue to grow. It's going to stop. In fact, it's going to shrink down. There must be some place it's going to stop. There must be some natural limit to the growth. And in fact, that's what economists like to call the equilibrium, right? So if we look at this growth, it's going to go up, 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 but then it's going to flatten out. And this flat line here is going to be the equilibrium level. So what we want to do is we want to understand, what is that equilibrium level? Well, let's think about it. What's going to happen in equilibrium? In equilibrium, the number of machines stays fixed. We stop growing. But what affects the number of machines? two things, right? One, investment. We buy new machines, right, based on our savings rate. What else? Depreciation. We lose machines to depreciation. So the equilibrium is going to occur when investment equals depreciation. Okay? Well, guess what? That's going to be easy to solve. This is why models are so great. Let's do this formally. So think about it. What's our output? It's just 10 times the square root of m. What's our investment? Well, that's easy, right? That's just 0.3 times 10 times the square root of m. So that's just 3 times the square root of m, right? What's our depreciation? Well, that's just m over 4. And in equilibrium, depreciation has to equal investment. So again, easy. We just get 3 times the square root of m equals m over 4. So that means 12 times the square root of m equals m. And if I divide both sides by the square root of m, I get 12 equals the square root of m. So that means m is going to equal 144. So if my total number of machines is 144, the depreciation is going to be actually exactly the same as the savings. So again, here's the math. The investment is 3 times the square root of n. Depreciation is 0.25 square root of m. I set those things equal, and I go ahead and solve, and I get 144 machines. Okay, nothing complicated. Let's just check. Okay, so we got 144 machines. What's my output? Well, it's just 10 times the square root of 144, so that's 120. Well, so what's my savings? How much do I invest in a new machine? Well, I take 0.3 times 120, which is 36 new machines. What's my depreciation? Well, that's 1/4 of 144, which is also 36 machines. So I invest in 36 machines wear out, so the total number of machines is still at 144. So 144 is an equilibrium. The number of new machines, the number of old machines exactly cancel out, and that's exactly where that curve finishes, right? Output is going to be at 120, right? So what we get is we get a long-run equilibrium in this model of exactly 120 units of output total. Okay, no wait, notice there's something ironic here. I called this a growth model. Well, what's ironic about this? What's ironic about this is eventually there's no growth, right? We're going to start with 4 machines, and then 9, and then 16, and then 23, and so on and so on and so on. Eventually we're going to take 144 machines, and then we stop. Growth stops. What's going on? Well, let's think about it. Depreciation is linear, right? So depreciation is just a nice linear function. But our output as a function of the number of machines is concave. That's falling off. So at some point, right, the amount of more output we're getting is falling to match the slope of the rate of depreciation, and those things exactly balance out. And that's why growth stops. Well, if growth stops, then the question is, how do we get more growth? Well, the answer is innovation. Innovation will allow us to continue to grow. And that's why people focus so much on innovation. So to get a real model of economic growth, we've got to move beyond this quote-unquote simple growth model and actually include a parameter, to even complicate the model even more, right? We've got to include a parameter that takes into account technological growth. So let's step back. What have we learned? We've learned that if we write down a simple model of growth, economic growth, that involves, investing money in new machines, right, but those machines depreciating, that there are limits to growth, right? That the model is just going to max out at this point where the number of machines lost to depreciation is exactly offset by the number of machines that we invested in the previous period. So growth is going to, start, if you start with no machines, growth will go really, really fast initially, but then it's going to fall off and reach this equilibrium level. So to get sustained growth, that's going to require new technologies, new innovations. And that's where we're going to go next. We're going to construct Solo's growth model, which includes this innovation parameter. Yeah, even more complicated, I know. But by including this innovation parameter, we'll see how growth can continue to be sustained. Okay, thanks.